Hey everyone, welcome, welcome. I'll be taking attendance in just a second. Welcome, everyone. Cool. Maybe I'll project my screen just so we can verify who's here. But I'm glad everyone's here. I think we're gonna still get a few more folks. We're gonna try to organize this. Like, if someone needs help in the first part, we're just gonna have to move through that. If no one needs help on the first part, then we'll just move on. So, I'm gonna mostly work in this process because I know everyone's at different locations and understandings. And welcome in everyone. So I'm gonna go ahead and put who I have here. So I got AJ came on in. We got Rebecca. Sorry, let me know Rebecca if it was one C or two C's. I always feel like I messed that up. And we got Rosario, Shannon, and then Zion. Let me know, did I miss anyone's name? Let me know if this is everyone who's here. Okay, one. Thank you. 1C. Perfect. And then I need help with everything. Okay, that's okay. That's anticipating. And just making sure we give some wait time for everyone to come on in. We're getting a few more folks. All right. Again, let me know if your name is missing from who we have currently here. But welcome everyone. So before we get started, things you should have open. I mean, you could have open if you want to log into the Desmos, you could totally do that to like go back to what your group did. Um, you should also perhaps have your big ideas. Actually, not perhaps. You should have this out because if you want to get proficient, at least proficient on your mini final, you want to make sure you try to reference the big ideas and how you're using it in your mini final. So I recommend having the big ideas packet open, and then again having your own mini final open, as well as any screenshots you took that you're trying to use on your mini final. Okay. Before we start, does anyone have any questions about the resources we should have open or anything like that? All right. Oh, let's see. Okay, great. So someone just needs some time for them to open them. Okay, so let me give you all some time to just get your resources open. And then it looks like, because I already got some feedback, that someone needs help with everything. So it looks like I'm going to be starting off with question one, and then from there. So, I mean, I understand that maybe some of you are probably just needing help on like a later question. But until that time comes, just feel free to jump on in. Otherwise, you could just, continue to work on your own mini final, process any questions you might have and things like that. Let me also put that in the chat. So things to have open. And then the question was, where's the big ideas packet? That is on Google Classroom, and it was asynchronous number 2. I'm also writing that down.
Hold up, Miss Donna. I have a question.
Yeah.
Okay, so do we get to screenshot our graphs and stuff in order for us to also get proficient on our final or no?
So I mean, screenshot, for example, you should have a model of your function. So there should be a graph, right? So at least it should have a model. Otherwise, you should be able to, like, if you don't want to have a picture, if you want to verbally explain it. But for example, see, we have our function here. You definitely want to
Mhm.
create a model of it, of the situation. And if you did not take your screenshot, I mean, you could just tell me what group you're in, and I could let you take your screenshot here as well, since I have access to that as well. So
Gotcha.
yeah, at minimum, you want to have your graph basically.
Okay. Thank you.
You're welcome, of course. Of course, it does make it stronger though. If you have other types of screenshots, I think you'll see later on when we start to discuss this more deeply. It does, help to have a screenshot. I'm gonna go ahead and make a copy of this so I could type. All right, so I'm hoping we're already here with our resources. So I put it also in the chat, things to have open, all your resources, such as Big Ideas Packet. That was asynchronous number 2 for period 6. Oops, and I think for the other periods it was another asynchronous, I think like 5 or something. So double check that. So this was for period 6. I gave it out a little earlier. The mini final and any screenshots you took with your group and your Desmos if you have access to your group Desmos. If you don't, just let me know and I could pop open your group Desmos and show you what your group did if you want to reference that as evidence. You could totally do that. All right, so let us begin with question number 1. So here I'm on my own copy. You all are going to be in your own copy because the first thing you want to do, of course, is read the question, right? So overall, you are actually a traffic court judge, right? So that's your role in this assignment. And you're trying to decide whether or not 2 math teachers are guilty of speeding because they did receive a speeding ticket from a CHP officer. The CHP officer claims that they were speeding because they went above 75 miles per hour. And you want to either refute that claim or actually verify that claim. And then it just goes on to the story of what the cops said. So they said they covered about 4 miles during that drive. At that point, they measured 75 miles per hour on the radar. So this right here is not evidence. So a lot of people are confusing like what the cop says versus what the teacher said as evidence. What you're going to be focusing on as evidence is actually on the provided function. You're going to use this function to prove whether or not the teachers were speeding at any point in their drive. So then again, Miss C says that's impossible. They acknowledge that their speedometer was broken, so that thing that kind of tells you when you're driving how fast you're going. But because she was riding on shotgun, because she was riding on shotgun, she had something else called an odometer, and it says reading every minute. So that means she was calculating the speed every minute. So like between 1 and 2 minutes, between 2 and 3 minutes. So she was kind of like using 2 points and calculating the average speed is what Miss C did. And according to Miss C, she says they never move faster than 75 miles per hour. You're going to analyze what Miss C did in question 3 in this mini final. But for the moment, just keep in mind that the speedometer was broken for the teacher. So they don't know exactly if they were speeding, but what we're going to be using is what Miss S has. So it says, besides, says the driver. So Miss S, I downloaded the odometer log for the whole drive, and it was followed by this formula. And this is the formula we're going to be using because that's the only, like, they downloaded that log. So this is actual evidence rather than a he said, she said, kind of argument. So we're going to base our evidence on this function. Keep in mind that D is distance measured in miles and T is measured in minutes. And that's why when y'all remember when we're in class, we had to multiply whatever answer we got by 60 because we want to convert it into miles per hour because otherwise we won't be able to compare whether or not they were speeding or going above 75 miles per hour. So that's just the little background of the task, just to kind of remind you. Okay, so now using our function, right, using that knowledge, what was the car's average speed during the 9-minute drive? So maybe someone in this group here, in this office hours, has an idea on how they got that first question. So let me know if anyone, you can use the chat or you can unmute, whatever. Let's see if anyone has any ideas on how you found the answer to number 1. Okay, we got some feedback here. There's a direct message in the chat. Let me go ahead and read it. We have, when I plugged in 9 minutes into the function, it resulted in 4.5 as the car's average speed during the 9 minutes, but I don't know if that's correct. And then Marcella's a public comment says, plug in units. Okay, so I heard plugging in is happening. Someone plugged in 9 minutes into the function and they got 4.5, and they believe that 4.5 is the speed. Marcella, specifically, what units did you plug in? So curious to know if you did the same thing that this other student did to get that average speed. If you don't know what else happened, that's okay. We're just trying to see if you do know what you did when you're talking about plugging in units. Did you also plug in 9, or did you also plug in something else? Okay, so in your group, you plugged in 9, 4, and 0. Okay. Do you remember why your group plugged in 4? 9, 4, and 0.
We plugged in 4 because it was the mile that we got.
Oh, okay. So because it was the mile that y'all got. Was it from here, like where it says this, about 4 miles during their time or something?
Yeah.
Ah, okay. So that's where that 4 came in. Okay. Awesome. Thank you so much, y'all, for sharing. So, first off, we're on the right track. We are going to plug in. That's correct. But let's go ahead and go to our big ideas packet and just see necessarily what do we need to do to find average speed. So, I'm going to go ahead and just go to my big ideas packet. Average speed is another way to just it's another way to say average rate of change. There's a lot of ways you can find the average rate of change, like average heartbeat, things like that. Average speed is an average rate of change. So I'm going to go to big idea number 5 to see what it tells us. Okay, so in order to find the average rate of change according to the big ideas packet, it says when you calculate the slope of the secant line that connects 2 points. So basically, what you need is 2 points. And once you have those 2 points, you're going to plug it into the slope formula. And that should give you either the speed. In this case right here, this example, it was a ball that was being thrown. We had a negative number, which means it's a velocity, because speed is always positive. So in either way, though, the first thing we need to do is we need 2 coordinate points, according to big idea number 5. We need 2 coordinate points, and we know that once we have those 2, we're going to go to slope formula. And in order to get those 2 points, maybe we do got to plug in to our function. So, whoops, go ahead and go back. So first what I'm going to write right here is big idea number 5. So just so you know, you want to reference this big idea when you're making your explanation. The reason for that is because this is about average rates of change, and it's telling us what to do. So this is the big idea you're going to reference for sure. Next thing is, some of you mentioned plugging in 0, 4, 9. I'm going to go ahead and pop open the graph that groups did. So first off, I do recommend putting a screenshot of your graph. There is a way to do this without using your graph though. So let's see. Whose graph should I steal? Neil's maybe? As long as they put it in correctly. So a lot of you said 9. Do y'all remember why you plugged in 9 to this function right here? Like, why is it a good thing to plug in 9 right here? So that means you did something like this. Let me just write out what that would look like. See, I'm just replacing all the T's with 9. And hopefully it gives us some answer. It does. It gives us some answer. Okay, so it was the distance. But then we have another person said 9 is a time, right? Let's go back to the what the description was, and let's see. So distance or time? Let's see. Let's go back here. Where do we see 9 at?
9 is the time.
9
The
is
amount of minutes they were driving for.
okay, so 9 is the time because that was okay, there we go. I see it here. They were driving for about 9 minutes. So 9 is the time. And I think it makes sense to plug in 9 for T, because if you look down here, it says T is time in minutes. So basically, for those of you who are plugging in 9, it's because you're plugging in the last point, right? Where their drive ends. So this point, I'm just going to go ahead and put, so that point is going to be represented by 9 comma, and the output was this. Maybe I'll just, let's see if I could copy and paste it. Right here. So that's where the drive ended, right? So that's when you plugged in 9, that's what you get as your output. Like, we don't really care what's happening after this because the teacher stopped their drive after 9 minutes. Okay, so we know, according to the big ideas packet, though, that we need not just 1 point, though. What else do we need in order to find the average rate of change? The start. That's right. So we put the start, and then AJ says 0, 0. So that's correct. So the start time, so the teachers, because they drove for 9 minutes, that means they must have started when T equals 0 minutes. So that's correct, AJ. Awesome. So for 0, 0, we actually don't need to plug in. You could if you want, but you can see it right here visually on your graph. If you click on it, it's going to tell you 0, 0. But you can, like, if you were more interested in plugging in, I could show you. All you would do is just go down here in a new column on Desmos, and you would just plug in 0, and then you'll see that you'll still get 0, 0 as your output. So you plug in 0, you get 0. So that's 0, 0. So that's your start, that's your end time. So what we've done so far is, first off, we used the problem's description, like what the teacher did, how long they were driving, and we have identified their starting point and their ending point. Now, let's just make sure we go back to the big ideas, because our goal is to find their average speed during the first 9 minutes, or during that 9 minutes of their drive. So it says here, okay, so we got our 2 points. Awesome. We got to now calculate the slope of that secant line that connects the 2 points. And in order to find slope, we're going to be using down here slope formula. So if you want to make connections to this big idea packet, you could imagine that you're connecting these 2 points with a line, and this line is called the secant line. And once you find the slope of the secant line, that's going to give you the average speed in those 9 minutes. And yes, some of you were asking about screenshots. I mean, feel free to take any screenshots that we're doing here in office hours, as long as, remember, you're going to be the one in charge of justifying and explaining, though. Because remember, just having this won't get you proficient. Just having this screenshot won't. But actually you describing and justifying what we're doing and why, and you understanding what we're doing here is what's going to get you proficient. You have to actually type out and explain. So that's why I kind of, when we go back to your own mini final, I just put a little note for you to make sure you explain, why are we using big idea number 5, and how is that helping us? Next thing you want to do is describe the steps that we're doing. Okay, so just making sure I clarify that. All right, so now we have our 2 points. I connected a line through them. That line is called my secant line. I now, according to the big ideas packet, have to find the slope. How do I do that? Does anyone have ideas on how I could find the slope here? Maybe you could use the chat, or you can unmute. Sorry, there's probably something in the chat. Let me just let other folks came in. Okay, so AJ, you said the slope tool thing. So actually the slope tool thing will be used for later. And then we have another slope slope tool. So AJ will come up later. Slope tool is not going to exactly give us the average rate between these 2 points, but don't worry, we will use that later. Someone in the chat, though, as a direct message said, using the formula m equals y2 minus y1 all over x2 minus x1. And that is accurate. And the reason for that is because if you look at the big ideas, see here, that's your next step. Once you connect your secant line 2 points, you go to the slope formula and you go ahead and you calculate the slope, and that's going to be your average speed. So that's correct, y'all. So we're going to be using that special formula, and in order to use it, let's label our points. I'm going to make the start x1, y1. And again, you want to make sure that you're either on a scratch paper or whatever, that you show your work here as well, that you understand how to, do the slope formula here. Or you could type it out if you're able to type it out. Okay, and slope formula is, so m equals y2 minus y1. Again, this is in your big ideas packet. And then all over x2 minus x1. And all we got to do now to find the speed, the average speed in that 9-minute drive, is to go ahead and substitute our numbers. And I know there was an additional comment in the chat. I'll make sure I address it. So let me pause here. There's 2 things. So we explained that we need these points to figure out how fast he was going and the time given, and that's why we plugged in 9. So I think it was teachers. So it wasn't just he. I think it was 2 female teachers, according to the thing, because there were Mrs. C and Mrs. S. And why we chose 0, 0, and then 9, 4.185 is, first off, you had to graph your function, the function that was evidenced right here. And then we plugged in 9 because that was the end of their drive. The teachers drove for 9 minutes, and that's why we plugged in 9 and got this point. You could have also just went to your graph and clicked at where 9, 4.185 was, and you wouldn't need to substitute. And I think AJ told us that the start time should be at 0, 0, because if they drove for 9 minutes, that means they started at time t equals 0. Or 0, 0. Again, if you were to just click on the dot on your graph, you would also see that. But I also plugged it in here to show everyone that you could also plug into your function and get the same thing. 0, 0 would be the start. For this one, it would be 9, 4.184. And then AJ says, do we just divide 9 by 4.185? And then someone said, I got 0.4655. Well, let's see. Maybe AJ, I think in the end, it will result to that. Let me go ahead and show everyone those step by step in case they don't see that. But let's see. So we got our slope formula. We're going to go ahead and plug in our numbers. So y2 is 4.185. Yeah, 1.85. And notice that that number is kind of rounded from what we see here, which is fine. Minus, and so that was y2. We have to subtract y1. Y1 is 0. All over. And we have x2 is 9. Minus, and then x1 is going to be 0. So I think that's what you meant, AJ. Like, don't we just divide those two? Because in the end, you're just subtracting 0. So that's correct. So it would be dividing 4.185 by 9, actually. Sorry, I'm going to go back to using black. So basically, y'all, in your calculators, can you please all check what do you get? Because we got someone said they got an answer, but we need to all double check this. Because subtracting by 0 doesn't really do anything. We're just going to get 4.185 divided by 9. What do we get? Go ahead and put that in the chat so we could double check what you all got. And welcome, Tori. Let me go ahead and put you in here for attendance. Let me know if anyone's missing on the attendance sheet. So I know someone got, yeah, welcome, welcome. Okay, great. 3 of you. Tori says a public comment, but 3 of you got 0.465, 0.465 repeatedly. That's right. So everyone else should double check that you get this. So 0.465. What was it? 465. But now we got to make sure that we understand what the units are in this problem. Yeah, 0.465. So what are the units? So in order to determine the units of what this is, first off, we remember that the top is your change in y. So our y values was basically here. This is our y. And our x values or our input is going to be t. So if anyone goes back to the problem, what did D represent? What did the output in this problem represent? Was it like, is it meters? Is it feet? What does the D represent? I do remember it represented some sort of distance, but like what was the distance? Perfect. So we got it represents distance in miles. That's correct. So I'm just going to put miles. All right. Can someone else remind me what did T represent? If you go to the problem, it did let us know what these T's represented. It says where T represents, and then that's going to help us determine what the units are here. All right, we have time, but one person specifically said it represents minutes. That's right. So we want to be specific here. Yes, it does represent time, but what kind of time? The T represented minutes. So the input represents minutes. And that's important because what that means is what we have is the top is your change in y, the change in distance. That's going to be miles. And it's going to say per minute, miles per minute. So that is the unit. So because we need to kind of make sure we compare this to miles per hour. Remember the cop says they were going above 75 miles per hour at some point in their drive. So we need to convert this miles per minute into miles per hour. So what can we do? Maybe some of you remember this from class. I probably are going to have to write it right here or something. Let's see if anyone has any ideas. So we got miles per minute, awesome, but I need to make sure we're in miles per hour so we could compare whether or not these teachers were indeed speeding. Oh, sorry guys. I didn't know there was some stuff in the chat. My bad. I was giving y'all some time. Okay, so three things are in the chat right now as a direct message. So we have multiply by 60 question mark. Do we multiply our miles by how long they drove, which was for 60 minutes? I love that. I love that. And then we have instantaneous rate of change. So at the moment, I mean, we are going to hit instantaneous rate of change, but for this particular problem, we are using big idea number 7, which is average rate. We're not yet going to hit instantaneous. All we want to do is just, we have miles per minute and we need to switch the units to miles per hour. So two of you mentioned multiply by 60. And I like the way the second person responded because they says, because we know that they drove, it says, because we multiplied by miles by how long they drove, which was 60 minutes. Okay, let's go ahead and explain it. So let's see, how do we kind of convert this into miles per hour? So let me get my little tool. So I'm gonna rewrite right here. Just gonna rewrite what we got. So we got 0.465 miles per minute. Miles per minute. You could also write it like this. I'm writing it like this because I'm about to do something that y'all probably remember. and we're going to multiply by, yes, we're going to multiply by 60. We know that there's 60 minutes. That's why I liked how that second answer said that. We know that there's 60 minutes in 1 hour. 1 hour. And I would definitely, by the way, y'all, I would definitely love to see this cancellation in your mini finals. But for example, y'all remember when we're doing Riemann sums, those rectangles, we're trying to find the units of the area under a curve. Very similar. Something will cancel out here when I multiply. Let me see if y'all know what cancels out here when I do this multiplication. Yay. We got two folks saying minutes. That's right. We get minutes that cancel. Boom and boom. Oops. Just cancel out. There we go. So then what that means is I'll be left over with miles on the top and in the bottom per hour. Divided by 1 doesn't do anything, but what we could do now is we're going to do 0.465 times 60. This whole thing got deleted, so you're just left over with divided by 1 hour, so it's not really going to affect our answer. Let's just go ahead and multiply these two. So 0.465 times 60. Go ahead and let us know what you get in the chat. See if y'all get the same thing I did when you multiply these two numbers. All right. Okay, yes. So 3 of you are following along with me. Perfect. Y'all got 27.9 miles per hour. That is correct. Again, if you didn't get that, please let us know. But yeah, so I also got the same thing. I just simply multiplied these two numbers and I got 27.9. And again, it's going to be miles per hour because those are the units that are left over. So it's just miles per hour. So if you look here on average, so in their 9-minute drive on average, they're not speeding. But I want you to remember that even though you're not speeding in your average drive, there could be times within your drive, there could be little spots that you could be speeding at. And that's later on in the later questions is when we're going to think about instantaneous rate of change, because this is an average. Instantaneous is going to be different. So this would be your answer to number 1. But remember, it's not about your answers. It's more so about you justifying your work and understanding and applying big ideas. There could be probably more big ideas if you want to make connections, right, to the big ideas packet. But for sure, and most importantly, big idea number 5. So again, I'm just going to make sure I put this plus justify the steps we did and just explain why. Again, why do we multiply by 60? Why do we use the slope formula? Again, all in your big ideas packet there. So I'm just gonna make sure I move this up. And I'm gonna also go back here just in case if anyone just needs to take a photo to just reference for later as you try to explain this for yourself. Go ahead and take the time to do that. And also let me know if there's any questions that are coming up for anybody. All right, cool. So I hope y'all took a screenshot so I could, or a photo, something to reference as you are typing up your own understanding of this and your own work. So remember, some of you liked the plugin method to determine the to start and the endpoint. Some of you liked where you just kind of just click on the graph once you graphed the function that was it Miss C or Miss S? Let me go back. Whoever got that function, it was Miss S. Downloaded the formula for the drive. So there's different ways to justify again. So I put both options on here. So up to you which one you'd like to use. But again, please make sure you make reference to the big idea number 5. All right, I'm going to go ahead and clear my screen. Then we could go ahead and talk about question number 2. And again, your job will be that you want to just type this out and explain this, on your own. But once you turn it in, I'll look at it. If it's proficient, awesome. If it's still not there yet, I'll give you feedback and I'll leave some comments and return it to you. And then you could just resubmit it. Later on, I think the primary focus will be for this mini final. So about asynchronous lesson number 3. So primary focus will be on this. If there's time, yes, because I know we end at 11:30. Yeah, if there's time, yes. If not, I do have tomorrow open office hours as well. So we could also have some time for that. Or you could text me and remind too, if we don't have time. All right, everyone. So now we talked about the average speed of the teacher's 9-minute drive. Now we're going to investigate what's the fastest speed that the car actually reached during this drive. So now we got to kind of investigate what's happening in between their 9-minute drive. So in order to do that, I'm going to go ahead and, so this was some groups thing. I don't know whose this was, but I'll just leave that there. Now I'm going to go ahead and kind of remind you of this, because this is going to help us kind of answer that question on where the fastest location would be. So if you read right here, it kind of first says that there's a graph of an ant that's moving, its distance and time, very similar to what we have for the teachers and their drive. It says, but between which of the 2 points is the speed of the ant the greatest, and between which 2 points is the slope the steepest? These two are basically asking the same question. So ant traveling the greatest speed is the same thing as the slope being the steepest. So what I did as a strategy to kind of figure this out is, well, in order to determine between which 2 points that's true, I'm just going to go ahead and draw secant lines. So this is a secant line between A and B. Let me actually change that color so that we can see it better. Make it green. So here is a secant line between A and B. And that's too light. Let's do it once more. And I'll just stick to it. There we go. So there is a secant line. Remember, a secant line is a line that connects any 2 points on a graph. Now let me do another line between B and C. And then one last line between C and D. So we look here, it probably is a little bit hard to tell because it's right on top of the graph, but if I try to scroll down, you can probably see much better. So this was between A and B. This is between B and C, and this is between C and D. So if you're looking at those, which would be the steepest? The first, second, or third line that I drew? What would you all say? Then I know, and then, okay, we have second, we have first. So we have either the second or the first. Someone else said number 1. And we could see what, and maybe if someone can explain, like, why is it the first, or why do you think it's the second? Okay, if no one knows, I'm gonna go ahead. This is how I like to imagine steepness. If I'm like hiking or something, I just imagine that I'm like walking, and whichever one, it's like the hike would be harder for me to walk on because it's very steep. So if I'm like walking, so I would look at this first line and it's pretty steep. It's pretty steep. I would hate to walk up this. It's a very steep line. But then when I look here, right, and I'm walking on here, it is steep as well. So the second one is steep, but it looks like it gets kind of less steep over time. Oops, as I'm walking, whereas this one, I kind of have to go up like this. So I'd have to work harder to kind of walk up that first line than I would for the second line. I know it's a little bit hard to tell. Like if you just look at these two, it almost looks like they're very similar, but I would also agree that for the first one, it is more steep. And again, I kind of imagine walking up a hill and it would be harder. It would be like harder because you have to like really use a lot of energy to walk up that hill. And then over here, obviously, it would be a breeze. I'll be walking. It's very less steep at this point. So yes, the steeper the slope, the higher the speed. So in this case scenario, the ant was traveling the fastest between the points A and B. So it was like traveling really, really fast, starts to slow down, and then ultimately slows even more down at the last point of its trip. So we're going to be looking at the slopes of the teacher's graph to determine at what point in their time was the speed the greatest, and we're going to try to figure out, well, what was that speed? And then we're going to answer that question for number 2. Let me go ahead and clear this. Let me know if anyone has questions about that, but that's also a reason why I stuck this in the Desmos. Another thing I stuck in the Desmos is, at which point is the instantaneous speed of the ant the greatest? And then I put recall instant speed of recall instant rate of change as the rate of change at an exact instant. So for this one, you can see there's a variety of different answers, but the instantaneous speed of when the ant is going the fastest is actually going to be very strongly related to when its average speed was the fastest. So we know from the previous answer that the ant was going the fastest between A and B, and then it starts to slow down. So I know that it either has to be at A or at B that the instantaneous speed is the fastest. And here's a strategy I like to do. What I like to do is I like to draw like a line that kind of approximates the slope of the point. So I'm just drawing like a line right at the point that's kind of like approximating the slope at that point. That's going to give us our instant speed. So then for B, it looks something like this. Then we have C. Then we have D, which flattens more out. So notice how instantaneous speed, it's like at 1 point as opposed to 2 points. So if I go down, oops, a little bit. I mean, I didn't let me go all the way down. And I wish I could kind of erase that green one so you don't get confused. No. I need to erase the green one. Well, okay, just look at the blue ones. I tried my best. Okay, look at the blue lines now. First, second, third, or fourth blue line, which one now looks the steepest? And this one's like, it's a little bit tricky. It's a little bit hard because for me, the slope at A and for the slope at B look similar. But let's see what y'all think. All right, so we have AJ saying the second one looks more steepest. I mean, I think perhaps I do see it a little bit angled more upward. See if anyone else has any opinion on this one. First, second, third, or fourth, which line would look the steepest? All right, okay, great. So we have another opinion that the second line looks the steepest. And let's see. We have either 1 or 3. So for 3, I would say this line right here isn't as steep as these two. Steep means it's like really angled up. Or again, imagine you're a person walking on these lines, like going up a hill. I would say it's either the first or the second one. And a lot of you are agreeing that the second one is more steeper than the first. I think I would agree. I feel like this is more shooting upward, and this one's kind of more like, it is going up, but it's not as fast. And then you could also compare back to your graph. Notice how at B, it looks like, for example, if the ant were walking, it looks like it's almost walking vertical. It's walking very fast here. And for A, it looks like it's just starting to speed up. So that's another way to think of it. But I would agree that at B, the instantaneous speed of the ant is the fastest. And I know there's a variety of different answers for sixth period. Again, we didn't really have time to cover this, but then now we know. So I would say at B as well, but it would be hard because A and B, either A or B would be fine as long as you can justify it. Okay. So all of that was due to the fact that we're going to go ahead and now try to apply this knowledge about slopes and speed into checking where the teachers were going the fastest. Once we check where they're going the fastest, we're going to try to calculate whether or not they were actually going above the speed limit or not. So there's this specific special tool. That's the thing I linked in the remind. So feel free to open that. I'm going to also go ahead and put it into the chat. And we're going to use this tool to help us out. So go ahead and open the tool. What you're going to see is you're going to see a lot of stuff that you probably don't understand, but I'll show you how to navigate this tool. Cool. So what you have in red right here is it's that function that teacher downloaded to represent their drive. And what you have here is it's a purple line that approximates instantaneous slopes at different points. So what you can do is you can play around and move this line, and you could kind of check where it's getting very steep versus less steep. And we're going to use the steepness of this purple line to kind of narrow down where the teachers would have been going the fastest. And you have to also keep in mind that they stopped driving at 9 minutes. So it's like we can't go past 9 minutes when we're checking the slopes. This is where we would stop. We could also zoom in. But different groups, I know at period 6, you all were just investigating, but didn't really get to answer. Yeah, you do want to open the Desmos with me as well. So yes, please open the little tool as well. You want to play around with that purple line. And you all just want to let me know at what point do you think the slope is getting the steepest. How you can tell me what point, by the way, y'all, is right here. So notice as I'm moving the tool, this is giving me the X value. So it looks like it's row number 5 right here. So it's telling me the X value right here, or you could like also click on the point as well. So again, just you could put it in the chat. Let us know at which point do you think the purple line is getting the steepest at in this 9-minute drive for the teachers. And again, remember, steeper slope is going to be where the teachers were going faster. So let me let y'all try it and then give me some feedback on where you think this is happening at. All right, we have some feedback here in the chat. Somewhere around 3 minutes. Can I, for a moment, I'm going to take out the red line just so that y'all can see. So somewhere around 3 minutes is around here. And I want y'all to notice how the graph does indeed kind of shoot up. Look at the line. It like really does shoot up here. So I agree. Somewhere around 3. Someone could argue that perhaps it's happening again over here. But once you hit over here, you're past 9 minutes. And remember, we want to just stop at 9 minutes. So I would totally say somewhere around 3, it looks very steep indeed. But now we got to narrow it down. Okay, somewhere around 3. We got AJ saying 3.18. So let me go ahead and move this tool to 3.18. So yeah, I see this purple line getting very steep. And I'm going to stop 3.18. What do y'all think? I mean, it looks pretty steep there. Would you all agree, or did someone else find a steeper point? I think I like it though. Let me know if anyone has other ideas, but I think this is a good point to stick with. Um, again, it's going to be an estimate, so it's not like there's going to be one perfect area where the slope is the steepest. All right, cool. So I don't think anyone else has any additional feedback to give. So let's go ahead and stick with AJ's point. Great. We've identified a point that's the steepest. Now, this isn't going to be like, I don't think we talked about steep slopes in our big ideas packet, but I would recommend that you use it. So right here for number 2, you want to reference the fact that the steeper the slope, the faster the speed. Because that's the thing that's kind of helping us determine at what location. So we determined at 3.18 comma, and it was 1.621. The teachers were going the fastest using the Desmos tool. So just make sure you include that. I'm just like making sure I am giving you all some stepping stones for your explanation that that's what we did right now, but we're not done yet. We still need to find the fastest speed. Similar to how we did for number 1, we need to come up with an answer that has miles per hours in it. Okay, so because for number 1, we were looking at average speed, what are we going to be looking at here? If I want to kind of figure out the speed at one point. So I want to figure out the speed here at x equals 3.18 minutes. What's a big idea I could use? So I want to figure out at that exact point in time how fast the teachers are going. Let's see if anyone knows there into the chat. Oh, sorry, I muted myself. Anyways, yay, two of you said we need to use the big idea of instantaneous rate of change. That is correct. So I'm going to also just make sure I write this down here. We're going to be using, and I don't remember the big idea, but big idea about instantaneous rate of change. Instantaneous rate of change, or you could call it instant rate of change. Let's go ahead and see which big idea that is. So we're moving on from big idea number 5, and it looks like it's big idea number 6 or big idea number 7. Yay, thank you, Shaylin. So let's see, big idea number 6. Okay, big idea number 6 tells us about like what is instantaneous rate of change. So I agree, big idea number 6. Big idea number 7 tells us how exactly to do it. And if you remember in class, what it is you zone in on a point that you want, and you have to choose your second point to be very, very close to that point that you desire, and then calculate the slope between those 2 points, if you see here. And that's going to give you your instant rate of change. So big idea 6 and big idea 7. So let's go ahead and just make sure you kind of make connections to those. Number 6 and 7, like when you're making your explanation. Perfect. Thank you so much. All right, so then, cool. We've identified a point. This is where it looks like the teachers are going the fastest. Now, let's apply the big idea of instant rate of change. So if we look at big idea number 7, how to actually do it. It says you can estimate and approximate the instantaneous rate of change by choosing points that are infinitely close to your point of interest. The point of interest is the point that AJ told us. That's where it was the steepest. That's our point of interest. So our second point has to be really, really close to that point. And then after that, we just got to find the slope of those 2 points. So yay. All right, what's a second point we can choose that's really, really close to this? We could just start clicking near it and just settle on a point that's really close. So if I click here, I get this point, but I don't know if that's close, 3.065. Maybe if I zoom in, yeah, it's gonna be better if I zoom in. So there's a variety of options y'all can choose here. There's many points. I mean, let's just try and go as close as we can. 3.175 look like it's really close to 3.18. What do y'all think? Should we settle here and just check this one? As long as that's our second point is really close, great. Okay, go ahead and take a screenshot because I feel like if I let go, this is gonna go away and it was very hard to grab this. And if someone can type out this in the chat, what this number is, that would be awesome. I'll let go once I see it in the chat. Thank you so much, Jalen. Awesome. And okay, let me go ahead and let me write down that second coordinate right here, just so that I don't lose it. So Shailene put that in the chat. So 3.175, comma, 1.6142. There we go. That way it's there for me. And my point of interest is also there. Yay. So I have it. There's a question in the chat. What does the other coordinate represent? So the second one, this one in red that we just found, that is us trying to apply big idea number 7. We know we have our point of interest, which AJ found, right, was at around 3.18. The slope was the steepest. We now had to choose a second point that was infinitely or very close to that point. That's what that second point represents. It's just another point that's very close to the point of interest. And why we're choosing that is so that we can estimate the instantaneous rate of change at that location. And instantaneous rate of change is very similar to how you find average rate of change, because as you can see, we're going to be using the slope formula again. The only difference between instant rate of change and average rate of change is the fact that for instant rate of change, your points are very, very close. So for example, in our big ideas, I don't really want to use this. I don't want to use this. I want to use this. The only reason I showed these in class was to show you that I had to just keep moving the points closer and closer. But ultimately, you want to choose 2 points that are very close, calculate the slope. That's going to be an approximation of your instant rate of change. So I'm going to be doing similar to what this last photo is showing us, 2 very close points. And that's how we can estimate it. Great questions. Let me know if there's any others. Let me go ahead and clear this. All right. Let me go back. Cool. So then now that we have our 2 points, if you remember right now that I just showed you big idea number 7, now what we got to do is do the same thing we did for number 1. We're going to find the slope between these 2 points. And because these two points are super close to each other, infinitely close, that means we're finding an instantaneous or instant rate of change at this particular moment. So let's see if they were speeding or not. Some of you already know what to do, so feel free to do your calculations. I'm going to go ahead and walk us, the rest of us who need some support. So we're going to again do the slope formula to find the speed. So I'm going to label this first one x1, y1, and the second one x2, y2. All right. And then, yes, we have a bunch of decimals, so be careful when you're using your phone and doing these calculations. So, okay, let's go ahead and do this. So we're going to do y2 minus y1 all over x2 minus x1. And then we're going to go ahead and plug in our values. So we have y2 is this number. So 1.6207 minus y1, which is going to be 1.6142, all divided by, and we're going to do x2, 3.18, and then we're going to minus 3.175. So for this one, we can't just do a quick calculation like we did for number 1. So that's a 7. We're going to go ahead and try this out on your own. See if you get the same thing I'm getting. I'm going to go ahead and subtract the two numbers. So I'm going to do 1.6207 minus 1.6142. And I got, for the top part, I got 0.0065. Remember, the top is miles. We're still in the same units all over. And then the bottom, I have to do 3.18 minus 3.175. And I got 0.005. And remember, we're still in minutes. T still represents minutes here. At the end of this, we do have to make sure we multiply by 60 again to convert. All right, again, you all should double check that you're getting this. The next move we need to do is divide these two numbers. And again, you want to verify that you're getting the same thing as I am here in these steps. I'm going to do 0.0065 divided by 0.005. Let me know what y'all get. I went ahead and got an answer, but let me know what y'all got. And then we'll nearly be done with this one, and we'll figure out whether the teachers were or not ever speeding in their drive. All right, so Marcella got 1.3. Let me know if anyone got anything different, but I also got one perfect. Someone else got 1.3 as well. I also got 1.3, so it looks like we're at 1.3 miles per minute. And then let's see, guys, in the chat, do you remember what do we do here so we could get miles per hour? How do we get this into miles per hour? Let me go to the slide. Multiplication. Oh, sorry. Let's see. Let me check out the chat. You cancel out the minutes. Yeah, minutes are going to cancel, but what do I multiply by again to get that canceling? Perfect. Thank you. Yes, we multiply by 60. And again, if you remember the setup, there's 60 minutes in 1 hour. So yes, minutes will also again cancel out here. 60 minutes in 1 hour. That's going to cancel out. You're going to be left over with miles per hour. And you're going to do 1.3 times 60. What do y'all get when you do that to determine the miles per hour? So it's multiplication. Let's see what you all get in the chat there. All right. What y'all got? 78? I'll trust y'all. I'm going to do 78 too. So I'm not going to do it in my phone. Did y'all round it? But I think it's pretty good. Okay, 78 miles per hour. So y'all, were these teachers at one point in their drive ever speeding? That means that we're going above 78, 75, my bad. Okay, that's good. I think 78 miles per hour is perfect. You're saying no, that's what. And then we have yes, they were speeding at some point, right? So notice how instantaneous rate is going to be different from average rate. So on average, teachers were not speeding. But if we were to zone in on where they were going the fastest in their drive, and from there we try to find the instant speed that they were going. So at any time, like the instant speed in their drive, we got that at some point for a very short time at around 3.18 minutes, they were indeed going above the speed limit. Yeah, so it looks like their fastest was around 75 miles per hour. So we're kind of already answering though. I mean, the answer for number two is 78 miles per hour, but we're also slightly answering number four when it's saying, are the math teachers guilty of speeding? I mean, first off, we're going to say, well, yes. Like you're going to say yes plus explain. And number three, remember our big ideas. Oh, sorry, we're talking about number two right now. We didn't do number three. I already put down the little notes for what we did for number two. Again, now it's your job to explain, show the work on it. And then number four, we kind of already know now that they were speeding. They went above 75 miles per hour. But go ahead and explain what we just kind of said. Like it kind of doesn't matter what they were doing on average. It matters what they were doing, like what their actual speed was at that exact moment in time, which is at around 3.18 minutes. It looks like they were going above the speed limit. So try your best to explain that. Like, um, okay, so there's still a clarifying question. So still being confused on how we got this point. So this point is basically a point that's very close to this point in purple that we chose. So step one, we've identified a point that was very steep, right? Now, according to big idea number 7, we have to choose a second point that's very close to that point, and then we're going to be able to determine the instant rate of speed at that point. So all we did is we chose a second point that was very close. You didn't even have to choose that point though. We could have chose another point that's really close. If I came in from behind it, I could have chose this 3.185 comma 1.6272. Or you could have chose another point that's a little bit farther but still kind of close, or even closer if you managed to. So that second point is going to be different for everyone, to be honest. So that's explaining that second point. And then what was the line made by putting the equation into Desmos? So the line as in the red line, yes, this one right here. But what I'm in right now is a Desmos tool that came from, so the red line right here, if I zoom out, that is the distance over time motion of the teacher's drive. So that's the teacher's motion. And this purple line, like to help us determine where they were going the steepest or the fastest, is actually a Desmos tool. That's the one I also put in Remind, but I could go ahead and put it back in the chat too. And yes, so the red line or the red curve was because we had to type out that equation. And then that purple line is from this tool. This tool kind of helps us see where the slope was the steepest. And at the steepest slope, that's where the teachers would be going their fastest speed. Let me know if there's more questions about what we, any additional questions about this one before we move on. I tried to zoom back into where we were, but it is gone. But here's the work. We still need screenshots. Yeah, trying my best to put it to where it was, somewhere there. Yeah, it's about as good as that would get, but it was flipped. Yeah. All right, any other questions on this? This is for number 2, and then also, y'all, this does touch on number 4 on whether or not the teachers are speeding, and we are concluding, awesome, yay, and we're concluding that yes, because we did find at some point in their drive, for like a very short time period, they were going a little bit above the speed limit. which isn't even that much. I mean, that's just like 3 miles per hour over it. It's not too bad. So clarifying question. So we used 1 point of interest and the other point closest to it as the 2 points, right? That is correct. That is us applying big idea number 7. The point of interest was found because that was where we located that the graph was the steepest. And then the second point, the one in red, that point, we just chose a point that was super close to our point of interest. And that one varies. So someone could have totally found an even closer point. So look at this, there's even closer points. See, because I zoomed in a little bit more, someone could have even chosen even better points. They would have got an even better estimate than what we did. But you could totally use the same 2 points that we chose together. So that's why that second point is going to be different for other people. But yeah, go ahead. Questions? Yeah, no problem. Yeah, I think it's because I started from number 1, number 2, and then now we're on. No, this is number 2 for sure. Can you explain this? Why the second point is necessary? Yeah, so in order to find speed, right, you need 2 points. You need to calculate the slope between 2 points to find speed. Like if you had just told me this was the answer, like this is the speed, that's not a speed. That is telling me at 3.18 minutes, I traveled a distance of 1.6207. That would not be an answer for a speed. We need another point to calculate the speed. In other words, we need another point to calculate the slope, which is this formula here. We need a y1, y2, and we need x2, x1, whatever. x1, y1, x2, y2. So we need a set of 2 coordinates. So that's why the second point is necessary. In addition, it's also necessary because if you go back to your big ideas packet, according to the big ideas, you can approximate the instantaneous rate of change by choosing points. You have to choose a point that's infinitely close to your point of interest. And our point of interest was that point that we identified was the steepest. So let me know if that answers that question, but keep them coming if there's still more questions about it. Awesome. Cool. Yeah, definitely. All right. About those things at all. Okay, great. So then we're saying, okay, let's go on to question. Oh, I'm sorry. Hold on. There's a lot of noise background. Give me a sec. Okay, sorry. I have a lot of stuff going on in the background, but anyways, yes, I will have this recording. Yeah, don't worry about that. That's just my little thing. It's getting ticked off with some movement outside. And then it says, would it be possible to do this without Desmos? I was just confused on how the equation correlates to the scenario. Yeah, so first off, how about, so I know not all of you were here at the beginning, so don't worry, I will upload this. I'll make sure this gets uploaded within the hour. So I'm gonna focus on getting this uploaded. Try to go back to when I first started this and see why did I even graph it and why am I using this equation? And then if you still got questions, come back tomorrow for that beginning part. Because I think at the beginning we explained why we want to actually graph this and the different ways you could actually do it. So the other way you could do it without the graph, I can answer that now, is if you substitute points into your function without the graph. But I did kind of say that the image of the function, it does very much help us to have that. So yeah, that's my suggestions for how to tackle that. But other than that, let me know if, yeah, perfect. Okay. Let me know if there's anything else. I'm going to go ahead and clear this up. Make sure you took a picture or something to help you guide you as you type out this stuff later. Make sure you do give yourself time to actually type out your explanations and then do submit this as well. And clear this up. Okay. Now, number 3 is the question that we want to do. So again, we kind of already tackled question 2 and also question 4. So it's just basically number 3. So it says, what is the fastest speed that Miss C could have possibly measured for the car if she applied her method correctly? So remember, Miss C was saying, no, we weren't speeding. But Miss C she was reading from something called an odometer. So let's see. So this is what Miss C says. Let's just go back to her. She said that, yes, the speedometer was broken in the car, but she was riding in the shotgun and she was checking the odometer. So I guess that's just another tool. I don't know what that is, honestly. If y'all know what that is, cool. I don't know. All I know is that this odometer is giving Miss C a reading every minute. That's all we got to know. So she's able to look at the speed, or she's able to get points at every minute, but she's not able to calculate instant speeds within a minute, like with decimal points. She's only able to do it per every minute. And she used that to calculate speed. And according to her, they never move faster than 75 miles per hour. So I don't think Miss C is lying. I mean, it could be true. So let's try to investigate. So she was only able to figure out the speed every minute. So for example, Miss C is not able to do what we did here. Miss C is not able to calculate an instantaneous rate of change. Because remember, instantaneous rate of change means the 2 points have to be very close to each other. Infinitely close is best. But Miss C was only able to do it with the 2 points apart by a minute. So that's what makes the difference in Miss C's method. So if we know that this point was the fastest speed, right? That means Miss C was able to calculate another point that is about a minute away from this. So we could choose a point that's a minute away. So I'm going to take out the red point. And we now need to find, either we could choose on the right or we could choose on the left. We have to just choose a point that's like a minute away. So it would be at 2.18, I guess. Y'all want to do 2.18, or we could do 4.18. I'm trying to find 2.18. It's way farther. It's going to be farther. So notice how I'm purposely just trying to choose a point that's a minute away from that point that we identified as the fastest, because then that would mean that Miss C calculated between that, minute. 2.18 right here. Should we use this one? These two are a minute apart. We could say, so Miss C calculated these 2 points when she was trying to figure out whether or not they were speeding. What do y'all think? Or should we go the other direction? We could also do 4.18. It doesn't matter as long as they're a minute apart. That's all the only thing that matters. Let's see the chat. Okay, good. So yes, 2.18. Awesome. Now, I just want to make sure I write this down. 0.574. There we go. So there we go. So Miss C, because she was only able to calculate speeds that are apart by a minute, she would only be able to calculate the slope between this, but she wouldn't be able to take this point and move it really, really close to that point of interest. Again, she's not able to do an instant rate of change. Miss C is only able to do an average rate of change. Average rate of change means the points are basically kind of far apart. They're not very close. Within a minute, a lot of stuff can happen when you're driving, right? You could actually be speeding within like in 15 seconds, but then you slow back down. So that's why her method isn't going to be that great. If you're just calculating it every minute, you can't really determine what's happening between the minutes. but we could go ahead and test what she would have gotten if she was trying to find the fastest speed by choosing these 2 points. You could also extend it and choose the other way if you want to kind of strengthen your answer, but we could go ahead and just do one. First off though, before I start to calculate the speed that Miss C could have found with these 2 points, does anyone have any questions about why we chose 2.18 or anything like that before we move on? And again, this is for number 3 about analyzing Miss C's method. Okay, I hope the silence means we got it, or maybe questions might come up after, and that's okay. So let's do this, y'all. Let's see the fastest. Okay, and there's a clarifying question. Are we trying to explain how she could have gotten the right answer? Well, actually, first, let's go ahead and so I would think that Miss C's method isn't going to be that great. And why? Because she's not able to find an instantaneous rate of change. So I think we're going to kind of prove that her method is not that great. Um, and she probably does not have the right answer. So that's what I'm guessing, because she's not able to find an instantaneous rate of change. It's going to affect it in that way. But let's go ahead and test it. Let's see what she gets. Let's try to find what answer she would have gotten. We're trying to kind of reason why Miss C is either right or she's wrong when she's arguing that they were not speeding. That's what we're trying to explain at this moment. And I guess we'll see once we calculate. A great question. Okay, let's do this, y'all. Let's figure this out. So let's go ahead and calculate the speed between these 2 points. And again, these are 2 points that Miss C could have recorded down and calculated to get what in her opinion would be the fastest speed, because she was only able to measure between minutes. All right, so we're gonna do y2 minus y1, or basically you could think of this as like top minus bottom. So I'm gonna do 1.621 minus 0.574. Then we're gonna do divided by my x2 is 3.18. Minus my x1 is 2.18. Remember, 1 minute apart. That's as best as Miss C could do because their speedometer was broken. Now let's go ahead and calculate and see what could she have gotten. And remember, we're still in miles per minute. So once we're done, we have to make sure we multiply by 60. So go ahead and try this out. I'm gonna also do some calculations here as well with you. Again, everyone's gonna come up with different answers. We're just coming up with this as a group. And there's many different ways you could do this while still being correct in your justification. This is what I got for the top. Oh yeah, then all over, this is just one since they're 1 minute apart. So boom. And I got miles per min. Okay, so I got 1.047. What do we do now? So we have miles per minute. I got 1.047 divided by 1 miles per minute. And if you didn't get that, just let us know. But what do we do next? We got to make sure we convert this to miles per hour. Let's make sure we know what to do. Yes, multiply by 60. Keep in mind, when you multiply by 60, the minutes cancel out. You're left over with miles per hour. So I'm just going to not write down that extra step, but if you need me to, I'm happy to. I'm just going to go ahead and multiply by 60 with just remembering that you know what's canceling out here. So I'm just going to multiply by 60 to tell us our miles per hour. So let's see, what's the fastest speed she could have recorded? Let's see what you all got. I got an answer, but I'm gonna see if you got the same thing. Let me know what y'all get. Okay, whoa, okay, 3 of you are saying 62.82. I think, yeah, I got the same thing. So Miss C was able to report that they were, oh, my pen went away. She was able to calculate that they only went 62.82 miles per hour. See how her method is not going to give her the fastest speed? Because she's only able to calculate between each minute. She's not able to do the instantaneous rate of change method that we did in number 2. So according to her, so she's not lying. It's not like she's lying to the judge. She didn't have a speedometer. So she said, okay, I actually calculated the average rate, but between each minute, because that's how much I was able to do. And according to my calculations, we never went over the speed limit. But the problem is, even between a minute, you can still go over a speed limit. So that is how you want to kind of explain that her method is gonna give her again, sorry, ignore that noise. I accidentally turned on my alarm and it gets what you call alerted, like even if a pigeon is walking. So my bad, I forgot to turn it off. I turned it on at night. So yeah, trying to see if I could turn it off from my phone or something. Or I could wait it out. Okay, it stopped. So let's just hope it doesn't get alerted again. Okay. So for number 3, when it says what's the fastest speed that she could have possibly measured for the car, and then if she applied her method corrected. So the fastest speed that we believe she could have gotten was around 62.82. I mean, up to you if you want to also check a minute after the 3.8, like 4.8, if you'd like to, you could do that, using the tool. But I think we already have enough evidence that Miss C is not going to be able to find the true fastest speed because she's not able to do big idea number 7. She's only able to do big idea number, what was the one about average rate? Let me go back. She's only able to do big idea number 5 is the flaw in Miss C's process. So let me just make sure. So Miss C is only able to measure between minutes. Sorry, is only able to measure a minute apart. Actually makes more sense. Not within a minute. And then you're going to explain what 2 points you used and what's the fastest speed you could have gotten. So I'll leave that as instructions for you. Explain what 2 points were used. And you could also explain why her method won't be effective. And there we go. And then again, these math teachers could have been like an algebra teacher who knows about average rates, but probably doesn't really know much about instant rates, which do make a difference, especially when it comes to even going slightly above a speed limit for a small time. But yeah, so yeah, that would be it, y'all. Let me know if anyone has any questions, but I think that's exactly right at the end of our office hours. I'm gonna make sure I do upload this though, as soon as I can. So I'm gonna try my best to do this now. Does anyone have any last minute questions or anything before you head off into lunch? Oh, sorry. Somebody needs me to go back to 3 to know what to put. Perfect. There we go. Yeah. Let me go ahead and clear the screen. I hope you all got that other work down. But yeah, so this is what to put there for your mini final. If no one else has any more questions, y'all are free to enjoy your lunch. Thank you so much for your engagement. Yay. I hope this was helpful. Yay. Thank you so much. Bye, everyone. Yay, that's great. Can't wait to see your works. Bye, y'all. Come back tomorrow, though, if you have more questions. I'll be here. All right, y'all. Let me know if there's anything. If not, enjoy your lunch. See you tomorrow or see you later. See you tomorrow. See you later. Bye, y'all.